Now, we may be given an equation in x's and y's describing a curve in the plane, and we might want to find a parameterization of that curve of the form x equals f of t, y equals g of t. This parameterization is not necessarily unique, and sometimes it's very easy to find such a parameterization. So if the curve we're looking at is defined by an equation y equals f of x, then it's pretty easy to find a parameterization. You let x equals t and y equals f of t, and this gives you parametric equations describing your curve. If the curve is of the form x equals g of y, then you can let y equals t and x equals g of t to get a parameterization of your curve. So let's try this with the parabola y equals x squared. I can let x equals t, y equals t squared. The domain of this function is all x values from minus infinity to infinity, so I can let the t run from minus infinity to infinity, and this traces out the entire parabola from left to right. Now suppose I want parametric equations describing the motion of a particle that starts at a0 and runs around the circle x squared plus y squared equals a squared twice in a counterclockwise direction, and it does that in the time interval between t equals 0 and 2 pi. And a here is not specified, but it could be 2, could be 3, could be 1. Each point on the circle of radius a here has coordinates x equals a times cosine, the angle that a ray from the point to the origin makes with the positive x-axis, and the y value is a times sine of that angle. And if I let xt equals a times cosine t and yt equals a times sine t, then this particle will just move around the circle exactly once in an anti-clockwise direction. But if I describe the angle as 2t, then as t ranges from 0 to 2 pi, the particle will move around this circle twice in a counterclockwise direction. So the parametric equations x of t equals a times cosine 2t, y of t equals a times sine 2t give me the path of a particle which moves around a circle of radius a in a counterclockwise direction, tracing out the path twice.